Dear learners, on behalf of Indira Gandhi National Open University, we welcome you for this textbook lecture session. Today's topic is steam power plant. I am Subhashish Maji, professor from School of Engineering and Technology of Indira Gandhi National Open University. Dear learners, let us begin our discussion on the topic steam power plant. After listening to this video lecture, you will be able to understand the concept of steam power plant. You will be able to know the steam power cycle. You will be able to explain the purpose of boiler, and also you will be able to solve the numerical related to steam power cycle. As you all know that energy is indispensable for our day-to-day life, but how we can generate energy, especially electrical energy, that can be done through different sources of energy. For example, if we consider the non-renewable sources energy like coal, oil, natural gas, we can have steam power plant where coal can be used as a fuel, and that coal is burned in the boiler. The heat evolved will be utilized for converting water into steam, and that high pressure, high temperature steam will enter into the turbine. Thereby, torque is generated, and the shaft of the turbine is coupled with the shaft of the generator, which in turn produces electricity, and the low pressure and low temperature steam coming out from the turbine will pass through the condenser where cold water is circulating, and the low pressure low temperature steam will give out the heat to the cold water which is circulating in the condenser. Thereby it will be converting into water, and the pump is there to send it back to the boiler and thereby complete the whole cycle. So today in our discussion we will discuss about the steam power plant. The steam power plant operating on the Rankine cycle is the most common thermal power plant operating with coal or lignite as fuel. The same steam power plant is used in nuclear power plant with the reactor replacing the furnace of the boiler as the heat source. A steam power plant consists of four important components. They are boiler, turbine, condenser and pump. The boiler generates steam at high pressure and high temperature. The high pressure, high temperature steam then passes through the turbine. The steam turbine converts the heat energy of steam into mechanical energy. The generator then converts the mechanical energy into electric power. Now, this is the schematic of steam power plant. You see that there are four components in this process. One is boiler, second one is turbine, third one is condenser, and fourth one is the pump. Boiler, here in the boiler coal is burned and the heat is generated. That heat is utilized for converting water into steam, and the high pressure high temperature steam then passes through the turbine. The expansion of steam takes place inside the turbine and the turbine shaft rotates. The shaft of the turbine is coupled with the shaft of the generator, and the generator in turn produces electricity. After the electricity is generated, that is being transmitted over a long distance, and after that it will be distributed to the end users. But today we will confine ourselves only the process which is occurring in steam power plant. This is the block diagram of the steam power plant. Here also you see the boiler which generates steam, turbine where expansion of steam takes place, there is condenser and the pump. So Q1 is the heat input into the boiler which is required for converting water into steam. After that, the turbine does work. So WT is the work done by the turbine. Then the heat is given out in the cooling water which is circulating in the condenser. So Q2 is the heat given out from the system to the outside. And of course, the pump is there to send water to the boiler pressure. And for that, WP is the work done onto the system, that is work done on the pump. Now, if you think of a control volume which is depicted in this block diagram with dotted line, here S is the control surface. Now, by sign convention, when you consider the heat input to the system is considered as positive and heat given out from the system to outside, it is considered as negative. So, in this process, Q1 is considered as positive and Q2 is the negative because it is heat loss from the system to outside. As far the work is concerned, the conventional sign convention is the work done by the system is considered as positive. Obviously, WT will be considered as the positive work and work done onto the system is considered as negative. So, WP will be considered as negative. With this sign convention, we will proceed further for the detailed discussion of steam power plant. We have seen the schematic of the steam power plant. Steady flow of water at high pressure enters the boiler. Heat transferred Q1 from the combustion of products generated by burning of fuel and air in the furnace and laid to the boiler causes the water to boil. The high pressure steam thus generated leaves the boiler steadily to enter the turbine. The steam expands in the turbine to deliver the shaft work. Here it is WT is shaft work done by the system. The low pressure steam leaving the turbine enters the water cooled condenser where it is condensed because of heat transfer Q2 to the cooling water which actually circulating through the condenser. A steady flow of condensate, that is water, enters the pump. To complete the cycle of events, the pump delivers water at high pressure to the boiler. The work supplied to the pump WP is usually very small in comparison to other interactions, and hence, unless otherwise mentioned, it is customary to neglect the magnitude of this work in the analysis of the steam power plant. Although each of the four devices in the plant, boiler, turbine, condenser and pump, is a steady flow device, all these four devices together enable water to undergo a thermodynamic cycle. The system, that is water, that undergoes the thermodynamic cycle is shown enclosed by the boundary S in the earlier figure which is shown in the block diagram. A careful perusal of the figure reveals that during the cycle there are four interactions across the system boundary, namely Q1, the heat transfer to the system, WT, the work output from the system, Q2, the heat transfer from the system, and WP, the work input to the system. As I already mentioned, by the sign convention, we can say Q1 and WT are positive, whereas Q2 and WP are negative. Applying the first law of thermodynamics to the system executing the cycle calculations, we can write that Q1 plus within bracket minus Q2 is equal to WT plus within bracket minus WP. Here we have already mentioned that Q1, since it is input to the system, it is considered as positive. Q2 is heat given out from the system, that's why it is considered as negative by sign convention. WT is the work done by the system, it is considered as positive. WP, that is work done onto the system, that's why it is considered as negative. So we can get Q1 minus Q2 is equal to WT minus WP. Now this equation comes out from the first law of thermodynamics for a cyclic process, which says that summation of Q is equal to the summation of W with proper sign convention. The performance of any device is usually evaluated by its efficiency. So here eta represents the efficiency, which is denoted as the ratio of the output to the input, and or we can also say that efficiency can also be defined as the ratio of what we want to what we are paying for. The output from the system power plant is the net work, that is WT minus WP, and the input is the heat transfer in the boiler, that is Q1. Hence, by definition, the thermal efficiency or the cycle efficiency of the plant is given by eta is equal to WT minus WP whole divided by Q1. Here the net output is WT minus WP and the input is Q1. That's why eta is defined as output by input. So efficiency is equal to WT minus WP whole divided by Q1. Also, in a thermodynamic cycle, from the first law of thermodynamics, net work, that is WT minus WP, is equal to net heat transfer, that is Q1 minus Q2. Therefore, it is obvious that the efficiency of the cycle is also given by eta is equal to Q1 minus Q2 whole divided by Q1 is equal to 1 minus Q2 divided by Q1. Here we have just substituted the value of WT minus WP is equal to Q1 minus Q2. This is another diagram for the steam power plant. Here you see the boiler which converts water into the steam. So here the coal is burned, that is shown at the bottom. The heat is taken by the water and the blue line is depicting it is the liquid phase of the working substance, which in this case it is water. Then it is converting into steam. After that, the high pressure, high temperature steam is passing through the turbine. The expansion of steam takes place in the turbine. Thereby, the work done for this is W dot turbine, and after that the low pressure, low temperature steam coming out from the turbine at the outlet then enters into the condenser. Here you see that there is a cold water is circulating through the pipes which is there inside the condenser, and heat will always flow from a high temperature region to a low temperature region. So in this case the heat is being transferred from the low pressure, low temperature steam to the circulating water. Thereby, it will be converting into liquid phase of the circulating substance. So, water is coming out from the point 1 and the pump is there to which is sending back the water in the boiler again for completing the whole cycle. Now, this is the TS diagram of simple power cycle. Now, whatever we have discussed that is depicted in TS diagram, we call it temperature entropy diagram. Here you see that the process which we have already discussed in the boiler is from 2 to 3. Here you see that 2 to 3 where the liquid, in phase of the working substance, that is water. First, it is achieving the temperature, say for example 100 degrees centigrade. After that, the temperature remains constant because here there is a change of phase takes place from liquid to vapor. But as you all know, when it is two-phase mixture, while change of phase takes place, the temperature and pressure remains constant. After that, it will be 100 degrees centigrade of steam. After that, even if you supply heat, that will be converting into the superheated steam. Here, point 3 is the stage. For this case, the pressure is 5 megapascal, and that is the entry point of the high pressure, high temperature steam into the turbine. And the turbine process is depicted from the point 3 to 4. Here the expansion takes place and the pressure will decrease, temperature will also decrease, and for this case the pressure decreased up to 0.005 megapascal. After that, the point 1 is the entry point of the boiler and 1 to 2 is the process occurring in the boiler. But in this case, the process occurring in the condenser is from point 4 to 1. So, 2 to 3 is the process which is occurring in the boiler. Point 3 to 4 is the expansion process within the turbine. Point 4 to 1, it is the process occurring in the condenser. Here it is condensed into the liquid phase, complete liquid phase at the point 1, and point 1 2 is the process which is occurring inside the pump. Now, in this case, this is another diagram of TS diagram. So, here what is going on, that the same thing is here. A to B is the pump work, and B to C up to D, it is the process occurring in the boiler. But there is a vertical line from D to the point which is connecting to the horizontal line at the in the cyclic process. But the vertical line represents the isentropic process, that is the entropy is constant. And but in actual case, the actual work done in the turbine inside the turbine is showing by the dotted line. And if you want to calculate the component efficiency of the turbine, then you can calculate the component efficiency of the turbine is defined as actual work by the turbine divided by the isentropic work. Now, this is another diagram, TS diagram of simple power cycle. Again, you see that point 3 is the entry point of the turbine. It is the point that is a normal cycle. Turbine starts with saturated vapor. It is not a superheated vapor, but since it is touching on the dome at the point 3, it is the saturated vapor. So, if you consider the normal cycle, the cyclic process will be 1, 2, 3, 4 and 1, and which is shown by the in the figure, and arrow is given for the cyclic process. But if you consider the water, the steam which is entering into the turbine at a superheated conditions, that is the superheat cycle, define turbines start with temperature and pressure at a superheated state, that is depicted in this figure at point 3 dash. So if superheated steam is entering into the turbine, then the cyclic process is 1, 2, 3, 3 dash, 4 dash, 1, 2. So there is a high pressure as given is depicted in the TS diagram, and low pressure is also depicted in the TS diagram. So this is the temperature entropy diagram. Why it is important? Because if you want to calculate the turbine efficiency, you have to calculate the turbine work. Turbine work is nothing but, in this case, if you consider the normal cycle, that is equal to H3 minus H4. If you consider the superheated cycle, obviously the turbine work in terms of enthalpy, change in enthalpy, that is equal to H3 dash minus H4 dash. What is the heat given out by the condenser? If you consider the normal cycle, that is equal to H4 minus H1. If you consider the superheat cycle, then the heat given out Q2 is equal to H4 dash minus H1. Pump work is H2 minus H1, and the heat input for the normal cycle is H3 minus H2. For the superheated cycle, it will be H3 dash minus H2. We will use this TS diagram for the analysis of the steam power cycle. Now, you have understood that the role of all 4 components, but boiler is a very important. So let us discuss briefly the boiler specification. So boiler make and year. XYZ is the make of the boiler, and it is manufactured in 2020. MCR, we call it maximum continuous rating, that is defined as, for a particular case, it is on the TPH, that is 10 ton per hour at the rate the steam is, continuously we are getting from the boiler. F and A, that is 100 degrees centigrade. So F and A means the amount of steam generated from water at 100 degree centigrade to saturated steam at 100 degrees centigrade. Type of boiler, 3-phase fire tube. Fuel fired is fuel oil and heating surface. For a particular case, we have taken that it is 1.45 meters square. Now, boiler type and classification. There may be fire tube boiler. So, when you consider a fire tube boiler, it means that fire in tube or hot gases through tubes and boiler feed water in cell site, and application used for small steam capacities up to 25 ton per hour and 17.5 kg per centimeter square pressure in gauge, that is a gauge pressure, and merits is low capital cost and easiness in operation. There is another type of boiler, we call it water tube boiler. So, when you consider water tube boiler, that is water flow through the tubes. Application used as process cum power boiler or power boilers, and steam capacities range from 4.5 to 120 ton per hour. Characteristics: high capital cost, used for high pressure, high capacity steam boiler, demands more control, calls for very stringent water quality. Now, when you consider the boiler, there is a heat balance. So, if you consider that after burning of fuel, you are giving heat input, and that is if you consider that is 100%. Ultimately, as an output from the boiler, you may get for this case we have considered that 69.1%. But what about 38.9%? That is the loss. 100 minus 69.1, that is the loss, and that losses are due to the different reasons. So what may be the losses? You know that when you use air for burning of fuel, the moisture will content in the air, and it is when air and takes place, air is participating in the burning process with the fuel, then the water which is there, the moisture in the air, that will be converting into steam, and that will simply go out with the flue gas. That is a loss. When you use coal, that also contains some moisture, that will also go as a waste along with the flue gases. And hot heat loss due to dry flue gas, that is also loss. And there may be some unburnt fuel, that is also considered as loss, and there may be the heat transfer from the boiler surface to the outside. So that is the heat loss due to radiation and other unaccounted loss. But for this case we have considered this 13.7%, that is the heat loss due to dry flue gas, 8.5 heat loss due to steam in flue gas, 2.7% is heat loss due to moisture in fuel, 0.8% is heat loss due to moisture in air, 3.4% that is heat loss due to unburnt in residue, and 1.8% is heat loss due to radiation and other unaccounted loss. But major loss is the heat loss due to dry flue gas, that is for this case it is 13.7%. Now let us discuss a very interesting numerical. Whatever we have discussed, we will see that how we can use for calculating the for the analysis of the whole process, that is the steam power plant. So the numerical is the steam enters a steam turbine at a pressure of 1 megapascal, a temperature of 300 degrees centigrade, and a velocity of 50 meters per second. The steam leaves the turbine at a pressure of 160 kilopascal and a velocity of 200 meters per second. Determine the watt per kilogram of steam flowing through the steam turbine, assuming the process to be reversible and adiabatic. That means the process is isentropic process, and while the process occurring in the turbine, it is an isentropic process. That means entropy is not changing, entropy is constant. Now when you solve any problem, it is better to draw the diagram, and you see that what are the data given for any particular problem. So if you draw the diagram for that particular component and jot down the data which is given for this problem, after that for solving the problem it will be very easy for us. So in solving this problem, it is usually advisable to draw a schematic and show the process on a TS diagram. So here the pressure at the inlet of the turbine for the steam is P1 is 1 megapascal, T1 is 300 degrees centigrade, V1 is 50 meter per second, and at the outlet of the turbine the pressure is 160 kilopascal and velocity is 200 meter per second. And one more advice is you have to draw the cycle diagram, then it will be easier for us to solve the problem. Now this is the cycle diagram for this numerical. So here 1 to 2 is the process which is occurring inside the turbine. So the turbine output, that is WT, is equal to H1 minus H2. So H1 we can get from the steam table. The pressure is given, temperature is given. So from the steam table we can calculate the value of enthalpy at point, that is H1. But how to calculate the enthalpy at the point 2? This is also very simple because since it is an isentropic process, so at point 1 the entropy is equal to the entropy at point 2. So S1 is equal to S2. But how to calculate S1? This is very easy because pressure is given, temperature is given from the steam table. You can get the value of entropy at the point 1. Now let us see how we have solved this problem. So we have to use the steady flow equation. This is a simple equation from the first law of thermodynamics. Q minus Wx divided by m is equal to del within bracket H plus V square by 2 plus Zz. So B square by 2, that comes out as a kinetic energy, Gz is the potential energy and H is the enthalpy. Now del means change in the whole thing which is there within the bracket. Also the flow is reversible and adiabatic, therefore as I already mentioned, the entropy at the point 1 is equal to the entropy at the point 2. So S1 is equal to S2. We assume that there is no heat loss since it is an adiabatic process, so Q is equal to 0. Therefore, per kg of steam, assuming the change in potential energy is negligible, so equation becomes minus Wx equal to within bracket H2 plus Vt square by 2 bracket close minus within bracket H1 plus V1 square by 2. So here H1 we can calculate from the steam table. V1, the velocity at the entry point of the turbine for the steam is given. V2 is also given, but only thing H2 we have to calculate. But how we can calculate? Let us see how we can calculate with the help of the isentropic process where S1 is equal to S2. At the entry point of the turbine, P1 is given as 10 bar, T1 is equal to 300 degree centigrade. Corresponding to the state from the steam table we can calculate H1, that is enthalpy at the point 1 is equal to 3052.2 kilojoule per kg, and S1, that is entropy at the point 1 is equal to 7.1251 kilojoule per kgK. At turbine exit P2 is given 1.6 bar. But we know very well, since it is an isentropic process, entropy at point 1 is equal to the entropy at point 2. So S1 is equal to S2 is equal to 7.1251 kilojoule per kgK. From this we can find the quality of the steam leaving the turbine. So there is another property, we call it quality. X is considered as the quality for this equation. So S2 is known, that is equal to 7.1251 is equal to X Sg plus within bracket 1 minus X Sf. Sg and Sf we can calculate from the value of Sg and Sf we can get from the steam table. So if we put the value of Sg and Sf from the steam table, we can calculate the value of the quality, that is X. For this case, it comes out to be 0.986. And H2 we can calculate by using the same type of equation, that is equal to X Hg plus within bracket 1 minus X multiplied by Hf. Hg and Hf we can get from the steam table. For the pressure P2, that is 1.6 bar, put the value of X, Hg and Hf, you can calculate the value of H2, that is enthalpy at the point 2, that is the exit point of the turbine. For this case, it comes out to be 2666.8 kilojoule per kg. Substituting these values in equation 2, we get minus Wx is equal to within bracket 2666.8 plus 200 square divided by 2 multiplied by 10 to the power minus 3 minus within bracket 3052.1 plus 50 square divided by 2 multiplied by 10 to the power minus 3 But dear learners, why we are multiplying by 10 to the power minus 3? Because H1 and H2 are considered as kilojoule, but when you calculate V square by 2, it is actually joule. So we have to convert into kilojoule. That's why for in this equation we are multiplying 10 to the power minus 3. So minus Wx will comes out to be minus 366.55. Therefore, minus W6 is equal to minus 366.55 kilojoule per kg. So work delivered per kg of steam is equal to 366.55 kilojoule. So dear learners, we have solved the numerical, and I have already suggested you, when you solve any numerical on steam power plant, my advice is first jot down the data which is given for that numerical. After that, you draw the cycle diagram and you see that what they are asking in the numerical. Then you just, if it is isentropic process, then the entropy will not change in the process which is occurring in the turbine. So at the entry point of the turbine, the entropy is S1, exit point in the turbine, the entropy is S2. So if it is reversible adiabatic or isentropic process, then S1 is equal to S2. So we have discussed the steam power plant in detail, and we have seen that there are 4 components in a steam power plant. One is boiler, second one is turbine, third one is condenser, and the fourth one is the pump. For if you consider all these 4 components together, then you can think of a control volume, and there is a control surface we have shown by the dotted line. After that, you see that what are the input with regard to the heat. So we are giving heat input Q1 and the heat loss Q2, that is in the condenser. And the turbine work is the WT, but net work is WT minus WP, because WP is the work done onto the system. You have to give, perform work onto the system. That's why the net work done is equal to WT minus WP. And the efficiency is very simple, that efficiency is nothing but output by input. So here the net output for this system is equal to WT minus WP, and the input is nothing but Q1. So we can calculate efficiency of the steam power plant. So let us summarize what we have discussed in today's discussion. We discussed the concept of steam power plant, we have discussed the steam power cycle, and lastly we have solved the numerical related to steam power plant. Here some suggested books are there, and these books are extremely good if you want to have a good idea or knowledge with regard to the thermodynamics, that P.K. Nag, that is the Tata McGraw-Hill Educations and Publishers, and one more very good book is mentioned over here, that is Fundamentals of Engineering Thermodynamics by Howell and Bacchus, and that is all publishers are McGraw-Hill Book Company. But today I have given a brief idea about the steam power plant, but there are so many ways we can improve upon the whole process. One is the reheat cycle, next is the regenerative cycle, and next another one is the binary power cycle. So we will discuss in detail in our next lecture sessions for the reheat cycle, regenerative cycle, and binary power cycle, and also the combined cycle. In the next lecture sessions we will discuss. So thank you very much for listening patiently for my lecture sessions that is on the topic of steam power plant. Thank you very much. And if you have any queries, this is my mobile number is there, my email address is there. You can ask any questions on this topic or any topic on this topic or any topics on thermodynamics, and we will love to interact with you through mail or through mobiles. And you know very well that there are two important laws are there on thermodynamics. One is the first law of thermodynamics. The first law of thermodynamics speaks about the conservation of energy, and you know very well that conservation of energy says that energy cannot be created nor destroyed. Total energy is always conserved. In this case also, we are getting the heat energy, but at what cost? We are using the fuel, that fossil fuel. Fossil fuel is considered as the non-renewable energy or conventional source of energy, and coal we are using for steam power plant. By burning up coal, it generates heat. That means we are converting chemical energy which is there within the coal is converting into heat energy. After that, the heat energy, it is after converting from chemical energy which is stored in coal to heat energy. Then again from heat energy to the mechanical energy we are converting in the turbine. Thereby the turbine shaft rotates. Then the shaft of the turbine is coupled with the shaft of the generator, which in turn producing electricity. So in that case again we are converting mechanical energy to electrical energy. So here you see that we are getting electrical energy at the cost of the chemical energy associated within the coal. And in this case, but so many things happening throughout the process. The chemical energy we can convert into heat energy by burning of coal, then heat energy again is converting into mechanical energy, because with a tremendous velocity the high pressure, high temperature steam strikes the blade of the turbine, thereby the turbine shaft rotates. So what we are doing, we are converting the heat energy into mechanical energy. But when the shaft of the generator is coupled with the shaft of the turbine, the generator actually producing electrical energy. So in that case we are converting mechanical energy to the electrical energy. So after that, the electrical energy after generating at the generating unit, we are transmitting the electrical power over a long distance, and so in that case that part you know very well that power is transmitted over a long distance at a very high voltage, so that the technical losses will be minimum. So that is the whole process. So thank you very much for today's discussion.